Let's say we're given some number n. How would we, as people here, determine if n is prime? Maybe the first method that we know of is just to try to factor this number. One idea is just to loop through. So loop through I is equal to 2 all the way up to something less than the square root of n. Okay. And see if that divides n. Okay. And there is an efficient algorithm to see if a number divides another, or if two things have a common prime factor. It's called the Euclidean algorithm. Or division, can pretty efficiently determine if I is dividing n. And so this is one algorithm, and maybe this is the algorithm that we would try if I give you a certain 3-digit number, say. But from a certain point of view, this is a really, really terrible algorithm. Because if, given this number n, I only need log 2n bits of information. I can write n out in binary, and that would take L bits, or L is log 2 of n. And this search going up to root n, this is something like root 2 to the L number of searches. Okay, so it takes this many operations, let's say, which is sadly exponential in L. And so from this point of view, this very naive algorithm is actually quite bad. And so the goal is to find a deterministic algorithm which provably determines if n is prime in time polynomial in L, okay, which is the size of the input if I were to input n as binary. Questions about the goal? Yes?
Are there ways that are not provable or determined, I guess?
Yeah. So I don't know the history too well, but there were many algorithms that existed before the one I'm about to tell you about that were either probabilistic or depended on, assume that you could search in a certain interval and that you would always be able to find a certain structure in there. For example, you would be able to find primes in a certain interval, or some other number theoretic phenomenon. And those structures do exist in those intervals, assuming the generalized Riemann hypothesis. Okay. So assuming the generalized Riemann hypothesis, there were many algorithms, deterministic algorithms, that ran in time poly L that determined if something was prime. But of course, we don't want to assume the generalized Riemann hypothesis. I will say though that this algorithm is basically never used in practice because those algorithms which do, whose proof does depend on the generalized Riemann hypothesis, those always run faster in practice. Okay. So in practice, I guess the generalized Riemann hypothesis is true. Okay. Okay. So let's begin with some basics. Hopefully, we have seen Fermat's little theorem before, which says the following: if p is a prime number, then for all a, okay, for all integers, a to the p is congruent to a mod p. In other words, we have equality in z mod pz, which I will abbreviate in this talk by FP. what is lesser known is a polynomial version of Fermat's little theorem, okay, which says that if P is prime, then for all A, x plus A raised to the P is congruent to x to the P plus A mod P. So in other words, we have equality in the ring Z mod PZ, or I guess FP. Adjoin the variable x. Okay. And of course, 2 implies 1 by setting x is equal to 0. Okay. So I'll just prove these. They form the heart of this algorithm. So here is the first observation, observation 1. If P is prime, then each binomial coefficient where the lower number is of this range is divisible by P. This is a triviality because if you expand this out, the numerator will have some P, and in the denominator you have some factorials of numbers which are strictly less than P. Okay. And there's no way to cancel out this factor of P in the numerator. And so this integer will be divisible by P. And surprisingly, with this one observation, all of these facts follow pretty quickly. So from this observation and the binomial theorem, we get this identity called the freshman's dream. That is what it is called on Wikipedia. It says that x plus y to the p is congruent to x to the p plus y to the p mod p. In other words, we have equality in fp adjoint xy. Well, in this case, using this identity, 1 actually implies 2 as well. Okay? Because 1 would tell us that this left-hand side is equal to x to the p plus a to the p. And then by applying this, we get that a to the p is equal to a. Okay? So we get that this is true. And for fun, even though probably all of us have already seen a gajillion proofs of Fermat's little theorem, let me just give you Euler's proof, since I thought it was quite cute. So you induct on A. Clearly, 1 to the p is congruent to 1 mod p. And then for k plus 1, you have k plus 1 to the p is congruent to k to the p plus 1 to the p by Freshman's dream. And k to the p is equal to k by the induction hypothesis. Very easy, very easy. Mod p. So both of these things are true. We have proven them. But what is important for us is that the converse of 2, converse to 2, is also true. And so now we finally have a characterization of prime numbers. So what's the proof of this? Well, suppose that x plus a to the n was congruent to x to the n plus a in z mod n z adjoint x. Okay. And in fact, we only really need to care about this for a coprime to n. So we can specialize the assumption, which was for all a, to just one particular a coprime to n. Okay. The binomial theorem, and comparing the coefficients of x to the k, tell us that therefore n choose I, a to some power, okay, which is that term in the binomial during expansion of this, must equal the corresponding term over here, which is 0. Questions about my slightly unorthodox choice of notation? Okay. And because A was chosen to be co-prime to n, by basic results in ring theory, we may divide A. And so, assuming this, we arrive at this assumption, okay, that for all I, 1 less than I less than n, we have this. Questions so far? Okay. Okay. Now let's assume that you have some p dividing n, where p is less than n. So in other words, I'm assuming that n is not prime. Okay. Then let p to the e be the highest power of p dividing n. Then we have the following: x plus 1 raised to the n is equal to x plus 1 raised to the p to the e times some k, right, the remaining portion of n. But this is equal by a number of applications of the freshman dream identity: x to the p to the e plus 1 raised to the k. Okay, and this is mod p. And so the coefficient of x to the p to the e, well, over here, what would that be? That's n choose p to the e. Okay. Well, what is that over here? That's precisely n. Sorry, I called it k. Okay. Something went wrong. What went wrong? Maybe. Why?
Well, you prove K equals 1 anyway.
Sure. Okay, sure. Thank you. We're fine. We're fine. And these are forced to be equal mod p. Right. And so this tells us that actually this is a contribution. Are there questions? Unfortunately, I slightly missed. Okay. No questions. So 2 is actually an if and only if. But this itself, checking this, will also take a long time. Okay? And the reason is because okay, well, let me first explain this. Checking this condition for all a, or for a co-prime to n, will also take a long time because computing this, I would expand out into a polynomial of degree n. Okay? So there would be n coefficients, and I would have to compute all of them. Okay? And so that would definitely take time, n, okay, which is not allowed. Right? We want something polynomial L. But amazingly, the very naive solution to fix this does work. Okay, so here's a theorem. Okay, fix an n an natural number. Okay, and suppose that for all 1 less than a and r less than, let's say, log base 2 to the 20th of n. Okay, which is polynomial in L. It's fine. A is co-prime to n, okay, and we have this condition, holding. Okay. But also, mod x to the r is equal to 1. Okay. So in other words, every time we reach a monomial of degree greater than or equal to r, we loop around. And so this cuts down the computation of this binomial theorem, binomial formula, to something of length r. And r is polynomial in L. And so this is efficiently computable. It turns out that assuming this, okay, then n is a prime or a power of a prime. Questions?
Sorry, what do you mean by mod x to the r is equal to 1? I'm sorry, I'm just not able to understand.
I mean that if you calculate this out, right, you'll get a big, long polynomial. And every time there's an x to the r, you can replace that with a 1. Every time there's an x to the r plus 1, you can replace that with a x. More ring theoretically, okay, you can say that these are equal in z mod n z, join x mod by x to the r minus 1. Okay, so in this quotient ring, that's also the same thing as saying this. But this is what you would think about computation. Okay. So this is the theorem that is the heart of the result. And so let me just spell out the algorithm for you, given that this theorem is true. So loop from 1 less than r less than log base 2 to the 20th. Okay, and then loop for a. Okay. Test if a is coprime to n. Okay. And you can do this by the Euclidean algorithm, which runs in time, O of log n. And of course, if a is not coprime to n, then n is definitely not prime. Okay. So if not, fail immediately. Okay. Otherwise, calculate x plus a to the n, mod n, and mod x to the r is equal to 1. Okay. And you can do this by dyadic squaring. So, for example, actually, I won't do an example. I would mess up. Okay. Safe to say that you can do this by squaring in a careful way. Okay. And this is also O of log n times r, let's say, because for each coefficient you need to write out, and it could be a number between 1 and n. Okay, so that takes log n digits, let's say, and there are r total digits that you have to worry about. And the squaring won't take much longer than that. Okay, questions? Okay, and then finally you check if this is equal to x to the n plus a. Okay, again, mod n is 0 and x to the r is 1. And if it's not equal, you fail. Okay. And finally, if you made it here, if you made it past these loops, okay, then n must be a power of a prime. How do you determine primality from this? You calculate, all the relevant 1 over kth roots, okay, where 1 is less than k is less than log n. Okay, and you can do this by some, iterative process. Okay, you can use Newton's method. You can use this Babylonian square root algorithm, which is you make a guess. Let's say r, and then your refined guess is the average of n of r and n of r, and this converges actually very quickly to root n. So you just compute for a while, you get a number, okay, up to a certain level of approximation, and then you compute the kth power of it. All of that is done efficiently. If that is equal to n, then boom, you found a power of a prime. If it's not, then it's not a power of a prime.
For that, or you just run the algorithm until you get a number, and then you're like, it's gonna be between these two integers, because it's likely gonna give you some.
Yeah, exactly. You run it until you get to the integer, and then you raise that integer to the kth power, and then that's fine. Okay, so the main point is that using this theorem, you get this like sort of really stupid algorithm that just implements the result and accomplishes the goal. Okay, so all that's left is just pure mathematics.
How can we compute what the actual rate is in terms of log? Like how many log base 2 of n's do we need?
Upper bounded by log to the 1,000. Okay, that's polynomial.
Sure.
Yeah.
The other algorithms that rely on the generalized Riemann hypothesis, whatever, do you know what the degree of those polynomials are?
Yeah, they're like, cubic or something. Quadratic, I don't know. This one, if you play the golf right, you can get it down to like 6. But I don't care about golf, and so it's 1,000. Okay, so how do we prove this main theorem? How do we prove this main theorem? Well, we will deduce it from 2 smaller claims. We will deduce it from this theorem. Fix n in n. Okay. Actually, let me write it on the very left board so that it might have an opportunity to sit there for a while. Theorem, fix n in n. Okay. Let R be coprime to n, and good. We'll figure out what that means later. Suppose, and also let's say R is less than log base 2n to the 10. Suppose that for all 1 less than A less than capital A, which is defined to be the floor of R times log of n, okay, A is coprime to n. And that dreamy expression. Okay, so I'm going to call this the dreamy expression. And this dreamy expression holds. Then n is a power of a prime. And then there's a lemma that says that there exists an R that is coprime to n. Good. And R is less than log base 2 n. Okay. Actually, I will remove this from this part. Leave that to the lemma. So with these 2 things, the theorem and the lemma, we will be able to prove this theorem.
Why is it 20 and 10? Or am I getting it that way?
It's because if R is log 10, okay, then I need to multiply by another log. And so the next best number after 10 is 20. So that's why it's 20.
I agree.
Thank you. Okay, are there questions about this theorem and this lemma? Okay. Yes.
Wait, what does good mean here? Sorry.
We'll find out.
Okay.
Okay. All that we need to know though is that there exists an R that is good. Okay. Yeah.
So back to this algorithm itself. When you compute these powers of n by repeated splitting, if you do it in a purely how much worse is it to do in a purely naive way versus presumably some more intelligent way that uses the fact that you have x to the r is equal to 1?
I don't know.
Because it seems like you have to do it pretty smartly to not kind of have it be really uncontrolled and have a lot of steps, right?
Yeah, so if you do it the naive way and compute x to the a to the n all the way, you need to keep track of all n coefficients of the thingy. But if you quotient by x to the r, you only need to keep track of r many coefficients. And then if you basically compute x to the powers of 2 and then multiply them together the right way, you only need log n many computations. Maybe 2 log n many computations.
Yeah.
So yeah, in both space and time, it becomes big O of, I guess, log n times r.
I guess that's one thing that every step you have to. Oh, I guess like you just multiply
Yeah,
and
yeah.
mod out by x.
Yeah,
plus
exactly.
one.
You mod out
Okay.
as you go.
do it in every step. Okay.
Yeah, that's true. Yeah. Okay, so let's do some math. Okay. Step 1. I'm proving this to 1. Suppose, for sake of contradiction, that n is not prime. Okay. So n is equal to some p times p, where p is prime, let's say. At a later step, I will make some warning here. At later step, we will realize that we really want p is congruent to 1 mod r. Okay. Sorry, p is definitely not congruent to 1 mod r. And we have some goodness is more than enough. To guarantee this. Okay. So this is a minor thing that I just flag at the very beginning. So by Fermat's by let's call this 1 and this 2. Okay. So by 1, all the primes that are dividing n, okay, are not in 1 through a. Okay. Which remember is r times log n. And so in particular, p will be bigger than r, and also p will be bigger than log to the n. Okay. Because we made sure that we cleared all of them. Okay. So recall from the Fermat stuff that p prime implies that for all a, x to the x plus a, p is this. Okay. So it is still it still is okay. So it is still true if I make the smaller quantification, only going from 1 to capital A, and also taking modulo x to the r is equal to 1. So, of course, if this is true, then with further restrictions, it remains true. Okay. So, for exponents, e is equal to p by this, and e is equal to n by this. Okay, I'll repeat it in a moment. We have that for all a from 1 to capital A, x plus a, that exponent is congruent to x to the e plus a. Mod p is equal to 0, and mod xr is equal to 1. So in other words, in fp adjoint x, mod x to the r minus 1. Okay. So this implies the result for e is equal to p, and this part, okay, where I furthermore mod out by p, implies this for e is equal to n. Okay. Questions about this? Okay. It's weird, it's technical, but it turns out to be like the heart of the proof. So these guys I'm going to call special exponents. Okay. So these are special exponents. Special exponents. Okay. Where the definition is they got to be coprime to r, which was the parameter over here, okay, and also satisfy this condition. Okay, questions? It is nonsense, and it will continue to get more nonsense. Okay. Step 2. I claim that D is also a special exponent. Okay, D is also a special exponent. D is definitely going to be co-prime to R, because D is a factor of n, and R is co-prime to n. So we need to check this condition. Okay. Okay, so let's check this condition. Let's recall some ring theory. Okay. So for let's say Q in some polynomial ring A adjoint X. Okay. We have an evaluation map Q from AX to AX, which takes in a polynomial and then plugs in Q as the variable of that polynomial. And this is a homomorphism. So evaluation is a homomorphism. True fact, very common used. In particular, we care about the evaluation at x to the e, okay, which is a map from, we're going to look at it from fpx to fpx. Okay. So let's compose this with a projection, or in other words, mod out this side by x to the r minus 1. Okay, that's fine. And so we map x to the r minus 1, that maps to x er minus 1. Okay. By definition of evaluation at x to the e. But in the codomain, x to the r is equal to 1. And so this is equal to 0. Because this is x to the r, which is 1, raised to the e, which is 1, minus 1, which is 0. Okay. And so by the universal property of quotients, this factors through to eval xe from this ring to itself. Okay, great. Finally, if E is co-prime to R, by very classical elementary number theory, Bezout's theorem, we have that x1 through xr is mapped to itself. Maps surjectively to x1 through xr. Okay, by this map, by substituting e x and e. Okay, if e is co-prime to r. And so actually, this is an isomorphism. If E is co-prime to R. Okay, it's an isomorphism, a ring isomorphism, if E is co-prime to R. And so now everything is easy. Okay, we did a small amount of abstract algebra, and now our life becomes.
You mean the bottom was
Yeah, sorry.
pretty good.
Okay. All right. We're close. Actually, that's not right. We're not close. To show D is a special exponent, consider x to the p raised to the d plus a. That, of course, is equal to x to the n plus a. Okay, which remember, because n is a special exponent, this is true. And this is x plus a pd. Okay, and then this is equal to x to the p plus a to the d. Okay, inside of this ring, fpx mod x r minus 1. And now we just apply the ring homomorphism, or the ring isomorphism xp, or the inverse of the ring isomorphism x to xp, to turn all the xp's into x's. Okay. And so this shows that D is a special exponent. Questions? One last lemma. If E1 and E2 are special exponents, then the product, E1 times E2, is possible. And I won't drag you through the proof, but it's really much the same thing. And you apply a certain isomorphism to turn the powers back into what they need to be. So I assure you this is an easy lemma from what the theory that I've already built up. So in particular, I'm going to define this funky E. E is the set of all p to some natural number times d to some natural number. Okay. So these stars represent arbitrary elements of the natural numbers. Okay. This is a monoid if anybody is interested. Questions? Okay. These are all special exponents. So I just put together all of these facts. Okay. So why do we care about these special exponents? Well, we'll see. Okay. So observe the following. Observe that because if E is a special exponent, then eval at x to the E, which we said was a ring isomorphism before, okay, agrees with raising to the power E. Okay, that's my notation for raising to the power E, which maps from fp adjoint x mod to itself. Okay, on the set P, okay, which is the set of polynomials P, which are defined as a product from a equals 1 to capital A of x plus a to some arbitrary natural number power. All of these guys are in Z mod, sorry, Z adjoint x, by the way. Is everybody okay with this so far? The reason is that eval x to the at x to the E plugs in x to the E here, right? And raising the whole thing to the power E has the E outside. But we showed, or the definition of special exponent has that the E on the outside of this parentheses can be dragged inside. Okay, so any like a linear factor like this, you can drag the E inside or outside if it's a special exponent. In other words, these two maps agree on this set of polynomials. It is nonsense, but it actually gets proves the theory. Okay, so this is the black box of ring theory that we need of field theory. It says that there exists a field, a finite field, F, which contains Fp, okay, that contains a primitive rth root of unity, which I will call zeta of R. Okay, so somewhere there is a field extension of Fp, and inside of F there is some zeta of R, so that zeta of R is a rth root of unity. Okay, and we now consider the following. Consider the set curly G, okay, which is the set of all evaluations P evaluated at zeta of R, where P is in curly P, which is defined here. Okay, so for all of these products of linear factors, okay, I evaluate them all at zeta of R. Okay, and this is going to be an element of F. Okay, So for example, an element of G might look like zeta of R plus 10 times zeta of R plus 3 squared. Right? This is an arbitrary element of G. Okay. We consider the set zeta of R raised to the E as all powers of zeta R raised to a special exponent. In other words, all zeta of R raised to the P to the some integer power times D to some integer power. Okay. And this will also be a subset of F. Okay. We can alternatively consider E bar to be the set E, which is defined here, mod R. So this would be a subset of Z mod RZ. Okay. So again, E consists of natural numbers. Okay, I can take their modulo of R, and they all land inside of Z RZ. And furthermore, because Z to the R, Z sub R, zeta R is a primitive R root of unity, powers agree if and only if they are equal modulo. Okay. So the two sets are related. Okay, but there's a bijection. You take E, a special exponent mod R, and you map that to zeta of R raised to the E mod R. Okay. And this is a bijection from E to zeta of R. Okay, this is bijection. Okay. In particular, they have the same cardinality. Let's say T. So T is equal to the size of zeta of R E, which is the size of E bar. Okay. We're almost there. Okay. So if you have been falling asleep, now is the time to observe something interesting at long last. Okay. Since A, okay, is bigger than 2R, remember that capital A was defined as R times log of n. Okay. So in particular, log n is going to be bigger than 2. This is bigger than 2 times T. Okay. Because T is a subset of Z or Z. Okay. Is bigger than T plus 1. Okay. So some crazy loss of, really, really not sharp inequality here. There are certainly, at least 2 to the T ways of picking a product P of strictly less than T of the linear guys, x plus 1 through x plus a. Okay. So there are at least T plus 1 of these, okay? And so I can choose any strictly less than T subset of these guys. And there are definitely more than 2 to the T ways of doing so. Okay. And now is the interesting part. Okay. This proof is actually an instance of what's called the polynomial method in combinatorics. Okay. It is one of the strangest methods in combinatorics. A notable, I remember something interesting. On Math Overflow, there was a question in which there was a problem asked, and somebody asked, could we solve this with the polynomial method? And then Terry Tao answered, I don't think so. And then a couple years later, the problem was solved using the polynomial method in like a less than 5-page paper. Okay. So the polynomial method is really, really tricky. Okay, it's really unintuitive, and sometimes it just requires crazy feats of definition work. But here's the punchline. Now, two distinct such P and Q, okay, where P and Q are both products of strictly less than T of these linear factors. Okay, so their degree in particular is less than T, have different evaluations. P evaluated at zeta of R is distinct from Q evaluated at zeta of R inside of this mega field F. Okay, let's see this. Why is this true? Suppose, for sake of contradiction, that we had such P and Q of small degree, so that P of zeta of R does equal Q of zeta of R. Okay. Well, then in particular, I can raise both sides to the e power. Okay, for any of for actually any e. Okay, but for my special exponents e inside of curly e, the e goes inside of the evaluation. Okay, so all of these are products of these guys. There's going to be e's flying about, and the e's go inside to attack the x's. Yeah.
So, why do you know they exist?
Why do I know what exists?
P and Q?
So P and Q are just arbitrary products of these linear factors of degree less than T. There are tons of them, tons of those. You can pick them off the street.
How do you know they're not equal at zeta of R? Sorry.
I'm proving this.
Oh, sorry.
So I suppose for sake of contradiction that actually they do equal. Then I can raise both sides to any special exponent e, where I can pull the e inside. Okay. Okay. So all this stuff about special exponents is just for this. Okay. All of that was just for this. It's unbelievable. And because zeta of R is a primitive R-third of unity, we have that all of these zeta of R to the e are distinct. For all the e inside of e bar. Okay, so e bar, which was e mod r, is specifically to kill off possibilities that zeta of r to a certain power are equal. Okay, so I kill them off, and now they're all the zeta of r e are distinct. Okay. And so what I have shown is that p and q have common roots on this set zeta r e, which has size t. And so I have shown you a degree less than t polynomial with t roots, with p minus q. Okay, p minus q is the polynomial in question, which is not going to happen. So this, I think, is the most interesting part of the proof, and all of that was just to set up this equal sign. Okay, so it's that's the payoff. Okay, and finally, I will prove an upper bound. Okay. Upper bound, step 5, upper bound of curly G, okay, which unfortunately I just erased. Even I have forgotten what G was. G is the set of evaluations P of zeta of R, where P is inside of this product of derivative stuff. So we showed that in that step, we showed that the cardinality of curly G was bigger than 2 to the t. Okay. Because there are at least 2 to the t many ways of picking these p, and all of them are distinct. And we will now show in step 5 that G is bounded above by n to the root. Okay. Consider small exponents. P to the I, d to the j, where I and j are less than square root of t. Okay. These guys are going to be inside of my curly E, which was the set of all arbitrary powers of P and T, which remember are is a subset of the natural numbers. Okay. This is a set of greater than T elements. Okay, this is a set of greater than T elements. Because there are this many choices for I and this many choices for J. And so I take projection from E to E mod R. There must be a collision. Because this guy has cardinality T. Right, so by the pigeonhole principle, another gem of combinatorics, okay, there must be collision. And so we must have E, sum E is equal to P to the I, P to the J, which is also equal to P to the I prime, D to the J prime, where I look modulo R. Okay. So E, which is this number in the natural numbers, and E prime, which is this number, are congruent modulo R. Okay. For I and J that are distinct from I prime and J prime. Okay. Both inside of this range. Okay, both inside of this range. And finally, I use, that n is not a power of P. Okay. One of the strangest uses of the hypothesis, okay, to imply that actually that this implies that E does not equal to E prime. Okay. So by uniqueness of prime factorization. Okay. Something like this. Okay. Okay. Thus we have found two distinct exponents. E and E prime inside of my special exponent set E, so that both of them are bounded by P to the root T, D to the root T, which is of course bounded by N to the root T. That agree mod R, okay, that agree mod R, which implies that zeta of R to the E is equal to zeta of R to the E prime. In F, which implies that for all of these evaluations inside of my curly G, okay, we have P evaluated here at E is equal to P evaluated at that, which is equal to this, which is equal to this, okay, in F. In other words, the polynomial x to the E minus x to the E prime, which is the polynomial in F, in Z adjoint X, okay, has root set containing G. Okay. And again, by an instance of the polynomial method, this guy, this implies that G must be bounded by N to the root, because that is the degree of this polynomial. Okay. Maybe I'll just finish proving the theorem and then leave the lemma as a, I don't know. The sixth and final step is where I finally use what good means. Okay, so that was something that I left untouched, and now we're going to see what that means. If we assume that n has order greater than log squared n, in this guy, z mod rz star, okay, So in other words, I'll write that out, i.e. for all 1 less than I less than log 2 squared of n, n to the I does not equal to 1 mod r. In other words, n to the I minus 1 is not divisible by r. Okay. In other words, okay, n to the 0, n to the floor log squared n, okay, are all distinct. Mod r. Okay, all of these facts are equivalent to this. Okay. Then t must be bigger than n to some arbitrary power mod r, which is inside of z mod rz x. Okay. Because these are all distinct special exponents, right? Mod r. And t is the cardinality of all the special exponents mod r. And this set is bigger than log squared of n. Okay. And now we get a contradiction with these inequalities. Right? So over here, we have that 2 to the t is less than or equal to n to the root t. And if t is bigger than log squared of n, okay, then we get a contradiction. And so the conclusion is that actually n must be a power of t. Okay, so extremely nested within this proof is this conclusion. Okay, that there does exist an R that is co-prime to n, and that is good in the sense that n has high order in this group, z mod r z star, turns out to be quite easy. But unfortunately, it seems like I don't have time. So I will leave it at that. Are there any questions for this really crazy polynomial method proof?
Is there any sense in which, like, this proof was in the air at the time?
No, I don't.
Is this completely?
Yeah, as you can tell, this proof, you know, if these guys had not discovered it, nobody would have discovered it. No, I can't say for sure. But it definitely took people by surprise. And it does, again, seem to be a trend that polynomial method proofs take people by surprise. They're often very short, very crazy, usually quite elementary, right? I didn't use anything beyond the, you know, some Rth roots of unity. So, yeah.
Historical question.
Yeah.
You said that there was the person on Math Overflow or whatever asked about polynomial method. Terry said no,
Yeah.
and it was
Yeah.
proven.
Yeah.
Was the person who asked the one who eventually proved
No,
it?
I don't think so.
Okay.
It was this De Vere finite
Oh,
thing.
okay.
Or you know some other you know capset bound. Maybe that was.
When was this?
When was this? 2002.
No, the Terry thing.
When was Terry's thing? That was proven in 2015, and then you know.
Right.
Oh, okay, that's not then. Finite field was like
The
2008.
I feel like
2008, 2009. Finite field.
Okay,
yeah.
then it was the capset problem. It was the capset problem. Okay. Yeah. Okay. I think this is it. The De Vere proof had shocked people. Okay, it was also polynomial method, and then somebody went on Math Overflow and was like, "Can we do more with this thing?" And then Terry was like, "Nah." And then somebody did more with it in 2015.
I bet that Overflow poster is kind of pissed then. He could have solved whatever the other thing was.
To date, that is my favorite Math Overflow post. Okay. Any other questions?
Let's thank the speaker.